For this video, we're gonna go through the solution for homework 10. So let's look at the first problem, 7.51. So we have a pump which is having the power of 28 kilowatts, and it delivers the water from point A to point C. The height difference from point A to point C is h, and the diameter of the part A is 20 centimeter. The diameter at point C is 11 centimeter. And the velocity at point C is 3 meters per second. Okay. And the head loss is equals to 2 times the velocity at point C divided by 2g. And the efficiency of the pump is 60%. The gamma of water at 20 degrees Celsius is 9700 Newton per cubic meter. So for this problem, we're gonna use the energy equation to find the relation between the point A and the point C first. So PA over gamma plus VA squared over 2G plus ZA. And because it's a pump, so it's on the right side, head of pump, equals to PC over gamma plus VC squared over 2G plus ZC plus the head loss. So PA is 0, VA is 0, PC is 0, and the difference between the ZA and the ZC is the term H. Okay, so the equation can be simplified by HV equals to VC squared over 2G plus H plus 2 times the VC squared over 2G. So the head of pump equals to 3 VC squared over 2G plus the height. So the next step is to find the pump head. So we are given the output energy. We know the gamma, we know the efficiency, but we still need to find the discharge of the system. So Q equals to VC times AC, which is 3 meters per second times pi over 4 times diameter at point C, which gives us 0.02851 cubic meter per second. Okay, so the power equals to Q times gamma times the head of pump divided by the efficiency. Okay, so the head of pump equals to the power times the efficiency divided by the Q and the gamma. Okay, The power here is given, which is 28 kilowatt. The efficiency is 60%, and discharge is 0.02851 cubic meter per second, and gamma is 790 Newton per cubic meter, which gives us 60.2 meter. Okay, so now we're gonna back substitute it to the energy equation. 60.2 meter equals to 3 times squared over 2 times plus the h. So the h gonna equals to 58.8 meters. Now let's look at problem 7.66. So we have an energy grid line shown in the picture, and we have something in the middle of the pipe. So the problem is asking what it could be. Is it a pump, a partially closed valve, an expansion, or a turbine? So when we look at this problem, the first thing we're gonna do is determine the direction of the flow. So because we have an energy grid line that's lower on the left side and higher on the right side, so it's increasing from left to right, so the flow direction should go from right to the left. Because of the friction loss, the energy grid line is always decreasing. So when we determine the flow direction is from the right to the left, we can know that the energy, because of the black box here, is actually decreasing. So that means this thing in the middle is extracting energy from the system. So it could not be a pump, because a pump is adding additional energy to the system. So we can choose B, C, and D. Now let's look at 7.71. So we have the hydraulic grid line and the energy grid line for pipeline as shown in the figure here. So the first problem is asking which one is the hydraulic grid line and which one is the energy grid line. So the energy grid line is the hydraulic grid line plus the velocity head. So of course the higher one, if there is velocity head, is the energy grid line. So for part A, the energy grid line is the solid one, and the hydraulic grid line is the dashed line. Okay, so the next problem is asking, are all pipes the same size? If not, which one is the smallest? So when we look at this figure here, we can see the difference between the energy grid line and hydraulic grid line is changing. That means the velocity head is different, which means the velocity is different in the entire system. And because the part from point A to point B, we have the highest velocity head, so which means the velocity is highest in this part. Therefore, it will have the most the smallest diameter. So for part B, A to B is the smallest. And for part C, it asking which of the region in the pipe the pressure is below the atmospheric pressure. So when we look at this figure from here, starting from here to here, we have part of energy grid line and the hydraulic grid line that's below the pipe. So which means we will have the negative pressure here, because the pipe itself kind of indicates the elevation head. So if the total energy is smaller than the elevation head, which means the pressure head needs to be 0. Okay, so therefore for part C, from point B to point C, we will have the negative pressure. And for part D, it's asking where is the point of maximum pressure in the system. For this problem, we're gonna first find the highest point of the energy grid line and choose which will be this part. Okay. Therefore, gonna look at the tank here, and of course the water surface only have the air pressure plus the, if it's pressurized in the tank, so it's air pressure plus the pressurized tank pressure. And at the bottom you can also have the water pressure above this point. So the highest point will be at the bottom of the tank. And part E, asking the minimum pressure in the system. So we're gonna find the difference between the pipe and the hydraulic grid line, where is the largest difference. So of course it will be somewhere here. So the minimum pressure of the system is at the band C. Okay. So the problem F is asking what do you think is located at the end of a pipe at point E. So it's this here. So we can see the velocity head actually increasing from here to here. So the velocity is increasing. That means we probably have a nozzle that's at the end of the pipe. And for part G, it's asking is the pressure in the tank above or below the atmospheric pressure. So when we look at this problem, if it's not pressurized, then the energy and the hydraulic gray line should starting at the water surface. Sorry, should be starting like here, okay. But actually, it's higher than the water surface. That means this tank is pressurized. So, so we're gonna say it's above the atmospheric pressure. And for part H, it's asking, what do you think is located at point B? So when we look at point B here, are we actually having a decreasing in velocity because the velocity head is smaller after passing this part, and we have kind of the energy gray line is dropping. Okay, so it should be an abrupt expansion. Now let's look at 7.74. So this problem, it gives us the head loss, which equals 0.014 L divided by D times V squared over 2G, where the L is the length of the pipe, D is the pipe diameter, assuming alpha equals to 1 at all locations. So the first part of the problem is asking us to find the discharge of the water for this system. So we're gonna use energy equation. So we're gonna define the point at water surface on the left as 0.1 and outlet at 0.2. We have the nozzle at the end of the pipe, so the velocity at 0.2 is actually different than the velocity in the pipe. So the energy equation will be P1 over gamma plus V1 squared over 2G plus Z1 equals to P2 over gamma plus V2 squared over 2G plus Z2 plus the head losses. Okay. P1 and V1 gonna be 0. P2 is 0. Z1 is 100 meter given in the problem figure. And Z2 is equal to 30 meters. The velocity V2 is still unknown here. And head loss is 0.014 L divided by D. So the L is 100 and 400 meters, so close to 100 meter plus 400 meters divided by the diameter, because they have the same diameter, that's why we can combine them together. 0.6 meters. Sorry, it should be times here. Over D and times the V squared over 2G. Okay. The V is not the V2 here, okay. But because of the continuity equation, V2 times A2 equals to V times the A. Okay, so V2 has the diameter of 0.3 meters. Which equals to V times the diameter, which is 0.6 meters squared. So V2 gonna equals to 4 times the velocity in the pipe. Okay. Now we're gonna back substitute it to energy equation. So 100 meter equals to 16 v squared over 2g plus 30 meters plus 0.014 times 500 meters over 0.6 meters v squared over 2g. And you solve for the velocity. Here it will be V equals to 7.046 meter per second. Okay, so we have the velocity here. The problem is asking us to find discharge, which the discharge will equals to A times V, and A is the diameter of the pipe, times the velocities, which gives us 1.99 cubic meter per second. And next part of the problem is asking us to draw the hydraulic and energy grid line of the system. So the energy grid line will starting at the water surface here, and well, because the entire pipe has a very straight forward, nothing is adding the energy or subtract the energy. The system and the pipe has the same diameter, so it will be a straight line like this. And for the hydraulic grid line, it will just minus the velocity head. Please notice the velocity head at the pipe is different than the velocity head at the nozzle. So we'll have a velocity head. We'll have the hydraulic grid line, which minus the velocity head from the energy grid line like that. So they are parallel until it reaches the nozzle part. It will increase. So here we will have the velocity head is larger than the velocity head at the starting point. And here this velocity head actually will be 16 times the velocity head of here. Okay, if here is the velocity head. Okay. And next part, we're gonna ask us to find the maximum pressure. So this will either at the tank of the bottom of the tank, or it will at the point of the nozzle. So for this problem, because we have an elevation 100 meters and the elevation which is 95 meters, so it will have only 5 meters of the additional pressure head acting at the bottom of the tank, and this value, which will be much smaller than the point here. Okay, because we actually have a kind of very high velocity head at the end of the system. So the maximum pressure point will at the point of the nozzle, Pmax, and the minimum point will be somewhere here when the pipe is actually higher than the energy grid line and hydraulic grid line. Okay, so here we will have a minimum pressure, therefore it will be negative pressure. That's why it will be the minimum point. So, the last part of this problem is asking us to find the minimum pressure of the system. So we're going to use the energy equation between the water surface and the highest point of the pipe. So P1 over gamma plus V1 squared over 2G plus C1 equals to P of the minimum over gamma plus the velocity at minimum, which is the velocity of the pipe, over 2G plus the elevation of the minimum point and plus the head losses of the minimum point. Okay, so P1 gonna be 0, V1 gonna be 0, C1 is given, which is 95, and C minimum is 100. Okay, so C1 is 100 minimum, which equals to P. Gamma is 980 Newton per cubic meter plus the velocity, which is 7.046 squared over 2G and C minimum is also 100 meters plus the head losses, which is 0.014, and the length of the pipe is 100 meters divided by the diameter, which is 0.6 meters times the velocity. Times 9. So when you solve for the P minimum, it equals to negative 82.6 kilopascal. Okay, and we're gonna do the similar thing between the point 1 and the pressure at the maximum location. So for that case, P1 over gamma plus V1 squared over 2G plus C1 equals to P maximum over gamma plus the velocity here is also the pipe velocity because it haven't go through the nozzle yet. We scroll 2G plus C maximum plus the head loss. So P1 0, V1 0, C1 is 100 meters, P max 0 Newton per cubic meter plus the velocity head. And the C maximum velocity, the elevation is only 30. And plus the head losses, for this case, the length will be 500 meters. Times the velocity head. So the P maximum is equals to 107 kilopascal. And if you compare the value and convert it to head terms, it will actually larger than the water surface difference between the here and here. So this is the solution for problem 7.74. Now we look at problem 7.76. So the discharge in the problem is given, which is equals to 1,000 cubic feet per second. The power generated with the efficiency of 85%. The total head losses is 4 feet, and the height difference h is 100 feet. So this is asking the power generated by the turbine, and I'm gonna sketch the energy grid line and the hydraulic grid line. So the first thing, we're gonna write down the energy equation between the point 1 here, water surface, and point 2 at another water surface on the other side. So P1 over gamma plus V1 squared over 2G plus Z1 equals to P2 over gamma plus V2 squared over 2G plus Z2 plus the head losses and the head of turbine. Okay, because the 2 points are at the water surface, so P1, V1, P2, V2 are zeros. The difference between Z1 and Z2 is 100 feet, so 100 feet gonna equals to the head losses, which is 4 feet, and turbine head. Okay. So our turbine head is actually 96 feet. So the power of the turbine equals to Q times gamma times the head of turbine times the efficiency. So actually equals to 100 cubic feet per second times the gamma, which is 62.4 times feet per cubic second times the height. Sorry, the head of turbine and times the efficiency. Notice this problem is in English unit, so when we do the calculation for power, we need to divide it by 550. So the power is actually 9,260. So now we're going to draw the energy grid line. So the energy grid line will starting at the water surface and decreasing because of the friction, or we can call it head losses, and then will drop because of the turbine here, and decreasing again before the entrance. And the hydraulic grid line will be the energy grid line minus the velocity head, and they also drop, and the hydraulic grid line will reach the height of the water surface. And the energy grid line here, because it enters a reservoir, or you can call it tank, you will lose the one velocity head energy, so drop to the water surface as well. Okay. So this is the energy grid line, this is the hydraulic grid line. So now let's look at the last problem 7.82. We have water flows from one reservoir to other reservoir. The discharge Q equals to 16 cubic feet per second. The head losses term L, general term 0.02 L over D times V squared over 2G. Please notice the L and D and V are different between the different pipes, and we have two different pipes connecting the two reservoirs. The diameter D1 and area A1 is given, same as the D2 and A2, because they call this pipe D1 and A1, the other pipe D2 and A2. So we're gonna call the two water surface we're gonna use for the energy equation S1 here and S2 here, in order to avoid the misconception between point 1 and point 2. Okay, so the first thing, we're gonna find the velocity of the first pipe. V1 equals to Q1 divided, Q is always the same, so it's the Q divided by A1, which is 16 cubic feet per second, divided by the area, which is 1 feet squared. So the velocity at first pipe is 16 feet per second. The velocity at second pipe is Q divided by A2, which is 16 cubic feet per second divided by 2 feet squared. So it will be 8 feet per second. Okay. So now we're gonna write down the energy equation between the two water surface. P S1 over gamma plus V S1 squared over 2G plus Z S1 equals to P S2 gamma plus V S2 squared over 2G plus Z S2 plus the head losses of the first pipe and head losses of second pipe. Okay, and please notice we are entering to the reservoir directly from the second pipe, so we will have another head losses, velocity head losses due to the entrance of the end of the pipe. Okay, so that will be loss of the outlet. So because we are selecting the two water surface, so the PS1 and VS1 is 0, PS2 and VS2 is also 0. So we will only have CES1 equals to CES2 plus the first head losses term is 0.02 L1 over D1 times the V1 squared over 2G plus the other head losses 0.02 L2 over D2 times V2 squared over 2G. Okay. And the head loss of the outlet will be same as the velocity on the second pipe, so it's V2 squared over 2G. So S1 equals to the N reservoir elevation is 110 feet plus 0.02. The first pipe is 200 feet in length and 1.128 feet in the diameter. And velocity is 16 feet per second squared over 2 times G plus 0.02. The second pipe is 300 feet plus divide the diameter, which is 1.596 feet. Okay, times the velocity, which is 8 feet per second over 2G plus the velocity head, L1 velocity head, 8 feet per second, 2 times 32.2 feet per second squared. Okay. So if we do the calculation, the elevation of surface 1 will be 129 feet. Okay. So now we can draw the energy grid line, which will starting from the water surface, decreasing like that. And because this has a smaller diameter, the slope of the energy grid line will be larger, and because the expansion also lost some energy here. And then we'll go to the next part. And for the second part, the energy grid line will have a smaller slope because it has a larger diameter of the pipe. The hydraulic grid line will be 1 V1 squared over 2G. Drop here. Here we will have V2 squared over 2G. Okay. And that will go to the water surface, and the energy grid line will lose one velocity head here. So this as energy grid line. And this is hydraulic grid.